Hey, this is Joe, and this is the 5th video in the 14th chapter of Stewart's Calculus, and we're going to be talking about the directional derivative and the gradient in this video. So, first off, we're going to be talking about directional derivatives. And directional derivatives, the use for them comes from the fact that both of the first-order partial derivatives in an equation with two independent variables, so del f, del x, and del f, del y, if we have a function f as a function of x and y, both of these partial derivatives, they show the rate of change in only two directions, so either along the x-axis or y-axis. And so that's useful for a lot of applications, these rate of changes in these two directions. However, a lot of the times, for a lot of different practical applications and theoretical applications, we want to find the rate of change of a multivariable function like this in a number of different directions. And that's where the directional derivative comes in. The directional derivative comes in because it allows us to calculate the rate of change in directions other than just parallel to the y or the x-axis. And so I'm going to give you the limit notation of the directional derivative right here, and then I'm going to show you a graphical diagram that kind of explains how this limit works. Then I'm going to give you a sort of more practical application for calculating directional derivatives. And basically what a directional derivative does is it calculates the rate of change of a function parallel to some other vector, or what we're going to use, a unit vector, in some other direction. So here's the limit notation. So this is the limit notation. And this right here means, this d means the directional derivative in the direction of the subscript vector u, where vector u is a two-dimensional vector ab, and so the directional derivative of f at point x sub 0, y sub 0 is equal to, the limit as h approaches 0, of f of x sub 0 plus h of h times a, y sub 0 plus hb, minus f x sub 0, y sub 0 all over h. And so what we get right here is we see that there's some limit being taken in both coordinates of f right here, unlike when we take partial derivatives where the h only appears in one coordinate. So that kind of indicates that there are going to be two components of two changes in components of the vector that are approaching 0, and that's kind of what gives us the directional derivative. But this limit notation, just looking at this, isn't terribly intuitive. I'll show you the graphical interpretation of this that kind of will allow this to make a little bit of sense, because there's some vector addition going on, since we are in fact taking the derivative of something in a direction of a vector, vector u. So let's take a look at that. So this is actually a diagram in your book, and so the slope of the line t right here is going to be the directional derivative of this surface S at point P in the direction of u, and you see how this tangent line t is parallel to vector u. And so the limit here, the reason we look at the limit as we were looking at it, for example, make f, inside the f we make we have x plus 0 plus, or sorry, not x plus 0, x sub 0 plus ha, and then the y coordinate of the vector first f is y sub 0 plus hb, is that ha and hb are the components of u if we make the magnitude of u h, in other words, approach 0. Because that's how derivatives work, right? We want that distance to approach 0. And so that vector addition makes it so that we can divide up the components of our function when we take the limit into h times a and h times b, and then add them to our initial x and y coordinates. So that's kind of the explanation for the limit definition of the directional derivative. But you're never really going to actually be using the limit definition of the directional derivative when you're taking directional derivatives. Now I'm going to go back and show you actually how you can go about taking directional derivatives practically. So this is the easiest way of going about solving directional derivatives. The directional derivative in the direction of u, where u is a vector divided into the components a, b, is equal to the partial derivative of x with respect to y times a plus the partial derivative of f with respect to y times b. Now, this is all fine and dandy. This is a really easy sort of thing to solve if doing your partial derivatives is easy as well. However, this looks like a cross product, right? Or not a cross product, sorry, a dot product. Because we have some vector, one component is being multiplied by something, and then added to the second component multiplied by something else. So it seems like we could express this as some vector del f del x, del f del y, and then dotted with vector u. And in fact we can. But turns out this vector right here is an important vector, and we actually have a symbol and a name for this vector, and we call that the gradient vector. The gradient vector of a function. And that's, as you can see, the other half of what this video is about. It's about the gradient vector. So the directional derivative can be expressed as the gradient of the function f dot product with the unit vector in the direction of which you're trying to find the derivative. And remember also, this is the general form of the directional derivative, because we have x's and y's in here. If you were to find a directional derivative at a particular point, you'd put in x sub 0, y sub 0, whatever the point is you're trying to look for, and you'd calculate the partial derivatives at those points. But now I'm going to go to the next screen and start talking a little bit more about the gradient and gradient notation, and then we'll come back to the directional derivatives in just a second. So, if we have a function with two independent variables, it exists and it's differentiable, then you say the gradient of that function f, and the little gradient sign is this kind of upside down delta right there, is equal to the vector, the first component of which is the partial derivative of f with respect to x, and the second component is the directional derivative of f with respect to y. Now let's say you have some function f with a sort of ambiguous number of components, so any number, so it could be you have x1, x sub 2, dot dot dot, x of n, and that's the n represents the number of components you could have. Then generally we can write out the expression of what a gradient is, because of course this is multivariable calculus. You don't just need two independent variables, we can do things with 6 independent variables. Then we'd write out that the directional derivative of the function of, and I'm writing this vector x right here, generally to symbolize all of the possible components that could be part of function f, and then that will equal the partial derivative of f with respect to the first component, or the first variable, I should say, the partial derivative of f with respect to the second, dot dot dot, however many you have, and then the directional derivative of f with respect to the nth term. And in this case, that would be the nth component, right? First component corresponds to first variable, second to second variable, and nth to nth variable. And so that's the form of the vector, of the gradient vector. And remember, the gradient is always a vector. And so now we can go back to our directional derivative talk, and we can write a nice little formula for the directional derivative of function f in the direction of u, and I'll just make this a function with two variables, and so we can say that that is equal to the gradient vector of f dotted with vector u, and that is our nice little expression for the directional derivative. But now the gradient vector is useful for more applications than just calculating directional derivatives. And throughout calculus you'll find more and more applications for the gradient vector, even in multivariable integral calculus, which is featured in Stewart's calculus. You find more applications for the gradient vector. But right now I'm going to mention two specific useful uses for the gradient vector. And the first is finding the maximum of a directional derivative. So finding the maximum of the directional derivative, you use the gradient vector to find that. And then also we can use it to find the normal vector of a tangent plane. So first we're going to start off with finding the maximum of a directional derivative, and we say the given some function, some multivariable function like this, and considering that it is differentiable, then the maximum of the maximum value of the directional derivative of f in the direction of u occurs when it occurs at I should say the magnitude of the gradient vector. And so remember, the magnitude of the gradient vector, since it's a vector, at that particular point, and so this x represents a particular point, so the maximum of this directional derivative occurs at the magnitude of the gradient vector. And this gradient vector, of course, we're talking about this gradient vector when it is pointing in the direction of u. And now for finding the normal vector of the tangent plane, if you remember, the equation of a tangent plane is z minus z sub 0 is equal to what's it? Oh yeah. So not a, del f del x at a particular point ab times x minus x sub 0 plus del f del y at a point ab times y minus y sub 0. And the way we can actually write this out, so you see we have a del f del x, del f del y. Those are two components of the gradient vector, and then you have a 1 right over here in front of the z's, which makes sense considering that you don't actually have the z values aren't changing if there's a function with only two variables. The z is the independent variable, right? So this means that we can actually write out the equation of a tangent plane as the gradient of f at some values ab dotted with x minus x sub 0. This vector right here, we can express it as a vector, y minus y sub 0, and z minus z sub 0, like that. And so this means that the gradient vector right here is equal to the normal vector of a tangent plane, right? Because remember, in our general equation for a plane, the coefficients of these x minus x sub 0, y minus y sub 0 are all components of the normal vector. So if the components of the gradient vector are those coefficients, that means that the gradient vector itself is also the vector that's normal to the plane, meaning that, to the tangent plane I should say. That means that the gradient vector is actually orthogonal to the tangent plane. So those are our two applications of the gradient right there. Now we're going to do a couple sample problems using both gradients and directional derivatives. Alright, so we're going to do number 23 on page 967 in your book, and given this function f sine xy, we're asked to find the maximum rate of change oh, sorry, I didn't mean to write that. The maximum rate of change of f and the direction in which this maximum rate of change occurs for the point 1, 0. So we know how to find a directional derivative, so that indicates the direction in which it occurs, and we also know how to find the maximum rate of change of a directional derivative, and that maximum rate of change is the gradient, the magnitude of the gradient. So what we should be able to do is find the maximum rate of change, which would be the magnitude of the gradient, and then work backwards to find the u, the u in the subscript of the directional derivative, in other words, the direction in which that gradient vector is going to point, the unit vector in which that is parallel to. So first off, what we need to start out with is finding the gradient vector of f and then the gradient vector of f at 1, 0. So first off, we're just going to find the gradient vector of xy, and so that's going to be del f, del x, and del f, del y. And this is a pretty easy function to take the partial derivatives of. The x component, if we take the partial derivative with respect to x, it's going to be y cosine xy. And the next component is going to be x cosine xy. And so now, what we need to do is we need to find that gradient vector at a particular point, 1, 0, and that will be 0, 1. And now we need to find the magnitude of that gradient vector in order to find the maximum rate of change, and that is going to be equal to root 0 squared plus 1 squared, and that's going to equal 1. So this is the max rate of change of f. 1. Now we need to find the direction in which that maximum rate of change happens, and in order to do that we need to use our directional derivative. But the thing is now we know what the gradient is and what the magnitude of the gradient is, but we don't know what the direction is. So we're looking for d subscript u of f of xy, and we're just going to do this generally to begin with. Well, actually, we can do this particularly. We're going to do the directional derivative in the direction of u at point 1, 0, and that is going to equal the gradient vector of f at point 1, 0, dotted with a certain vector u. And now we need to remember our properties of dot products. We know that a dot product can be expressed as a quotient using a cosine function, namely the magnitudes of both of these multiplied and then multiplied by the cosine of the angle in between them. So we're going to get the magnitude of the gradient vector at 1, 0, and we've already found that. And then we're going to get the magnitude of vector u, which we don't know. And then we're going to get times the cosine of the angle in between them. And since we want our directional derivative to point in the direction of u, in other words, we want our gradient to point in the direction of u, they should be parallel, so there shouldn't be any angle in between them. The angle should be 0. So this is going to be cosine 0. So the magnitude of the gradient is 1. We don't know the magnitude of vector u. And then cosine of 0 is also 1. So the directional derivative right there, the magnitude of that is going to be equal to just the magnitude of the unit vector, which, it being a unit vector, is presumably going to be 1. But in any case, what we can do is we can say, okay, we can express this unit vector right there if we consider u to have components a, b. We can express it as a squared plus b squared, all square rooted. And then we know that it has to be equal to 1 because it's a unit vector. And what we can do is actually bring this bit down and work out the dot product as we would without, in its other definition, using both the components here. So the components of the gradient are 0 and 1. So we'd have 0 times a plus 1 times b. So that means that goes away, and so we have b is equal to root a squared plus b squared, like that. And then that means b squared is equal to a squared plus b squared, and then that means that a squared is equal to 0. So that means we don't have any x component for our u vector, since a is going to be 0. And since we know that the magnitude of u has to be 1, that means that the only other way to make that magnitude 1 is make the other component 1, make b equal to 1. So therefore b has to be 1, and so our direction vector, our u vector, is going to be 0, 1. Like that. So now we have the two things that we were looking for. We have the greatest rate of change of function f is going to be 1, and the direction in which that happens, in which that maximum rate of change happens, is going to be parallel to this unit vector, 0, 1. So there you go. That is how kind of one of the simplest but also most powerful problems using the gradient and the directional derivative. Now let's go on to do another problem. So now we're going to do problem 28 on page 968 in your book, and given this function of x and y, we're asked to find all the directions in which the directional derivative of f is equal to 1 at point 0, 2. So first thing we're going to need to do is find the directional derivative of f of xy. We don't know what direction we're finding it in. That's actually what we're going to end up trying to find, and so we need to get the gradient f of xy dotted with some vector u. And so we need to find the general gradient. So first we're going to have to find the partial derivative with respect to y, and that's going to be equal to negative y squared e to the negative xy, and then we're going to have to find the directional derivative with respect to y. That's going to be negative yx, you have to use your product rule here, to the negative xy plus e to the negative xy, dotted with vector u. And now we want to find this, and so now that we have the general form right here, we're going to have to find, since we're finding this for a particular point, 0, 2, we want to find the directional derivative at 0, 2, so the particular one. And that is going to give us negative 4, 1 for our gradient vector, dotted with u, and because this is a function in terms of two variables, we will consider u to have components a, b, so that'll be dotted with some vector a, the components a, b, and we're looking for this directional derivative for what values of a and b will this equal 1. And so we'll expand this out and we'll get negative 4a plus b is equal to 1. And this is the equation that we're trying to solve. However, we have another constraint right here. We have the constraint that u be a unit vector. In other words, the magnitude of u, so root a squared plus b squared is equal to 1. So we have to satisfy that condition as well. Now we have both equations that are equal to 1. We can make these, the left sides, equal to one another and solve for that. So we're going to get negative 4a plus b equal to root a squared plus b squared. We move the square root over and we distribute everything, and we're going to get a 16a squared minus 8ab plus b squared equal to a squared plus b squared, and then we will get a 15a squared minus 8ab equals 0, and then that will reduce down to 15/8 a is equal to b. So, given an equation like this, what we have is an equation for all of the solutions, to all the possible solutions to this equation right here. In other words, any two values of a and b that satisfy this equality, that satisfy this ratio, and of course also satisfy this equation, but they will naturally when they satisfy this ratio right there, all those values will be possible directions in which the directional derivative will be equal to 1. So for example, one of those possible values of u, and I'll call that u sub 1, is 8/15 and 47/15, like that. That's one possible value, just for example. And so you can calculate out a bunch of those. So that's it for this video. Stay tuned for the next video when we start optimizing multivariable functions and surfaces, and then the video after that about Lagrange multipliers. That's going to be our last video for this course. So get excited for that. Thanks for watching.